National Electrical Code Section 250.24d addresses using a cold water pipe as a grounding electrode conductor for subpanel. This is permissible under specific conditions. Firstly, the subpanel must be located no more than 6 feet from the grounding point on the cold water pipe. This 6-foot rule is a crucial aspect of the code. Secondly, the grounding electrode conductor must be connected in a manner that ensures a permanent and effective ground. The connection must be reliable and maintain its integrity over time. Thirdly, the cold water pipe must be metallic and in direct contact with the earth for 10 feet or more. This ensures a sufficient grounding path to the earth. If the subpanel is located more than 6 feet from the grounding point on the cold water pipe, the bond must be run back to the main panel. In such cases, the cold water pipe cannot be used as the sole grounding electrode for the subpanel. Additional considerations include the grounding electrode conductor sizing, which must be in accordance with Table 250.122 of the National Electrical Code. This table provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the ungrounded conductors. The connection to the cold water pipe must be made with a listed clamp. Using a listed clamp ensures that the connection meets safety standards and is suitable for the intended purpose. The cold water pipe must not be used as a grounding electrode if it is coated with non-conductive material. A non-conductive coating would impede the flow of electricity and render the pipe ineffective as a grounding electrode. There is an exception. If the subpanel is located in a metal enclosure that is bonded to the main service panel grounding electrode system, the bonding conductor to the cold water pipe may be omitted. In this case, the metal enclosure provides an alternative grounding path. It is always best practice to consult the latest edition of the National Electrical Code and local codes for specific requirements, as code requirements can vary depending on the jurisdiction. To elaborate further on the requirements, the 6-foot rule is in place to minimize impedance in the grounding path. Impedance is the opposition to the flow of alternating current. A longer grounding conductor introduces more impedance, which can reduce the effectiveness of the grounding system. By limiting the distance to 6 feet, the National Electrical Code aims to ensure a low impedance grounding path. The requirement that the cold water pipe be metallic and in direct contact with the earth for 10 feet or more is intended to provide a reliable connection to the earth. The earth acts as a large reservoir of electrons and provides a path for fault current to return to the source. The 10-foot requirement ensures that the cold water pipe is in contact with a sufficient amount of earth to provide a low resistance grounding path. The grounding electrode conductor, as mentioned, must be sized according to Table 250.122. This table takes into account the size of the ungrounded conductors and the material of the grounding electrode conductor. Using the correct size grounding electrode conductor is essential for ensuring that the grounding system can effectively carry fault current. The listed clamp requirement is intended to ensure that the connection to the cold water pipe is mechanically and electrically sound. A listed clamp is a clamp that has been tested and certified by a recognized testing laboratory to meet specific safety standards. Using a listed clamp provides assurance that the connection will not loosen or corrode over time. As previously stated, a cold water pipe must not be used as a grounding electrode if it is coated with non-conductive material, because the non-conductive coating would prevent the flow of electricity from the electrical system to the earth. If the pipe is coated, the grounding system would be ineffective and could pose a safety hazard. In the exception, where the subpanel is located in a metal enclosure that is bonded to the main service panel grounding electrode system, the bonding conductor to the cold water pipe may be omitted because the metal enclosure provides a grounding path. However, it is important to ensure that the metal enclosure is properly bonded to the main service panel grounding electrode system. This bonding can be achieved by using a bonding jumper or other approved means. The information here is for general guidance only, and it is not a substitute for consulting the National Electrical Code and local codes. The National Electrical Code is a comprehensive set of standards for electrical installations, and it is essential to consult the latest edition of the National Electrical Code to ensure compliance with all applicable requirements. Local codes may also have additional requirements that are not covered in the National Electrical Code. Therefore, it is important to consult with local authorities to determine the specific requirements for electrical installations in your area. When working with electrical systems, it is essential to take all necessary safety precautions. Electrical work can be dangerous, and it is important to be properly trained and qualified before attempting any electrical work. Always disconnect power before working on any electrical equipment, and use appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician. An electrician has the training and experience to safely and effectively install and maintain electrical systems. Now let's delve deeper into some of the specific aspects of grounding and bonding. Grounding and bonding are two distinct but related concepts. Grounding is the process of connecting an electrical system to the earth. Bonding is the process of connecting different metal parts of an electrical system together to create a low impedance path for fault current. The purpose of grounding is to provide a path for fault current to return to the source. When a fault occurs, such as a short circuit, current will flow through the grounding system back to the source. This fault current will trip a circuit breaker or fuse, which will interrupt the flow of electricity and prevent a fire or electric shock. The purpose of bonding is to reduce the voltage difference between different metal parts of an electrical system. When a fault occurs, the voltage on different metal parts of the system can rise. If there is a significant voltage difference between two metal parts, a person could receive an electric shock if they touch both parts at the same time. Bonding helps to equalize the voltage on different metal parts, which reduces the risk of electric shock. There are two main types of grounding systems: grounded systems and ungrounded systems. In a grounded system, one of the conductors is intentionally connected to the earth. This conductor is called the neutral conductor. In an ungrounded system, none of the conductors are intentionally connected to the earth. Grounded systems are more common than ungrounded systems. Grounded systems provide a lower impedance path for fault current, which makes them more effective at preventing fires and electric shocks. Ungrounded systems are sometimes used in industrial applications where it is important to maintain power even during a fault. In an ungrounded system, a single fault will not cause a circuit breaker or fuse to trip. This can be advantageous in situations where it is important to keep equipment running, even if there is a fault. However, it is important to note that an ungrounded system is still susceptible to electric shock. If a person touches a faulted conductor in an ungrounded system, they could receive an electric shock. Therefore, it is important to take extra precautions when working with ungrounded systems. In addition to grounding and bonding, there are other important safety measures that should be taken when working with electrical systems. One important safety measure is to use ground fault circuit interrupters or GFCIs. A ground fault circuit interrupter is a device that detects ground faults and interrupts the flow of electricity. GFCIs are required in many areas such as bathrooms, kitchens, and outdoor locations. GFCIs can help to prevent electric shocks by quickly interrupting the flow of electricity when a ground fault occurs. Another important safety measure is to use arc fault circuit interrupters or RFCIs. An arc fault circuit interrupter is a device that detects arc faults and interrupts the flow of electricity. Arc faults are a type of electrical fault that can cause fires. RFCIs are required in many areas, such as bedrooms and living rooms. RFCIs can help to prevent fires by quickly interrupting the flow of electricity when an arc fault occurs. When working with electrical systems, it is also important to use the correct wiring methods. The National Electrical Code specifies the types of wiring methods that are permitted in different locations. It is important to use the correct wiring method for the location to ensure that the electrical system is safe and reliable. In addition to using the correct wiring methods, it is also important to use the correct size wire. The size of the wire must be sufficient to carry the current that will be flowing through the wire. If the wire is too small, it can overheat and cause a fire. The National Electrical Code provides tables that specify the allowable ampacity of different sizes of wire. Finally, it is important to properly terminate all electrical connections. Electrical connections must be tight and secure to prevent them from loosening over time. Loose electrical connections can cause heat and arcing, which can lead to fires. Therefore, it is important to take the time to properly terminate all electrical connections. By following these safety precautions, you can help to ensure that electrical systems are safe and reliable. Remember, electrical work can be dangerous, and it is important to be properly trained and qualified before attempting any electrical work. Always disconnect power before working on any electrical equipment, and use appropriate personal protective equipment. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician. Let's consider a hypothetical scenario. Suppose you are installing a subpanel in a detached garage. The detached garage is located 20 feet from the main service panel. In this scenario, you would not be able to use the cold water pipe as the sole grounding electrode for the subpanel, because the subpanel is located more than 6 feet from the grounding point on the cold water pipe. In this case, you would need to run a grounding electrode conductor from the subpanel back to the main service panel. The grounding electrode conductor would need to be sized according to table 250.122. You would also need to install a ground rod or other grounding electrode at the detached garage and bond it to the subpanel enclosure. The grounding electrode conductor from the main service panel would then be connected to the grounding electrode at the detached garage. This would provide a complete grounding system for the subpanel in the detached garage. As another example, let's say you are installing a subpanel in a metal enclosure inside of a house. The metal enclosure is bonded to the main service panel grounding electrode system. In this scenario, you may be able to omit the bonding conductor to the cold water pipe because the metal enclosure provides a grounding path. However, it is important to verify that the metal enclosure is properly bonded to the main service panel grounding electrode system. This bonding can be achieved by using a bonding jumper or other approved means. You should also consult with local authorities to determine the specific requirements for grounding subpanels in metal enclosures in your area. Again, remember that these examples are for illustrative purposes only. It is important to consult the National Electrical Code and local codes for specific requirements. The National Electrical Code is a complex document, and it is essential to have a thorough understanding of the code before attempting any electrical work. If you are unsure about any aspect of the code, it is best to consult with a qualified electrician. Electrical safety is paramount, and it is important to take all necessary precautions to prevent fires and electric shocks. The National Electrical Code is designed to provide a safe and reliable electrical system, and it is essential to follow the code to ensure the safety of people and property. Furthermore, consider the specifics related to overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are essential components of an electrical system. These devices are designed to protect the electrical system from overcurrents, which can cause fires and electric shocks. Overcurrents can occur for a variety of reasons, such as short circuits, overloads, and ground faults. When an overcurrent occurs, the overcurrent protection device will trip, which will interrupt the flow of electricity and prevent damage to the electrical system. Circuit breakers are reusable overcurrent protection devices. When a circuit breaker trips, it can be reset by simply flipping the breaker switch to the on position. Fuses are non-reusable overcurrent protection devices. When a fuse blows, it must be replaced with a new fuse of the same size. It is important to use the correct size overcurrent protection device for the circuit. If the overcurrent protection device is too small, it will trip unnecessarily. If the overcurrent protection device is too large, it will not protect the electrical system from overcurrents. The National Electrical Code provides tables that specify the allowable ampacity of different sizes of wire and the maximum size of a current protection device that can be used with each size of wire. When selecting an overcurrent protection device, it is also important to consider the interrupting rating of the device. The interrupting rating is the maximum amount of current that the device can safely interrupt. The interrupting rating of the overcurrent protection device must be greater than or equal to the available fault current at the point where the device is installed. Available fault current is the amount of current that would flow if a short circuit were to occur at that point. The available fault current can be calculated using a variety of methods. It is important to select an overcurrent protection device with an interrupting rating that is sufficient to handle the available fault current. Otherwise, the overcurrent protection device could fail to interrupt the fault current, which could lead to a fire or electric shock. Proper grounding and bonding, combined with correctly sized and installed overcurrent protection, are the cornerstones of a safe and reliable electrical system. Consulting the National Electrical Code and adhering to local codes are critical steps in ensuring that an electrical installation meets all safety requirements. Always prioritize safety and seek the expertise of a qualified electrician when needed.